Hi, my name is Mark Boxer, and I'm with Tony Ostrander. We are both with OFS, and we're going to give a presentation today on fiber deployments, some starting questions for munis and co-ops. And so there are a couple of questions with new builds, and two of them are just how do you build it, with what types of cables, and then also what kind of network architecture do you use. And we're going to talk about some of those choices and give some of the various pros and cons of different scenarios. But before we do that, I wanted to give a little bit of background on OFS, our employer. So we are with OFS, and if you look on the left-hand side of the screen, you can see a timeline. We can trace our lineage back to Alexander Graham Bell. And the way I normally describe us as a company is that we are basically the fiber optic arm of what was Bell Labs. And so if you look at the map on the right-hand side of the screen, you can see various operations around the globe. And a couple of them in specific. Our corporate headquarters are in Norcross, Georgia, and this is a picture of our plant in Norcross, Georgia. That's a suburb of Atlanta. And then we make a lot of our cable in a place called Carrollton, Georgia, which is about 70 miles to the west of Norcross. So as far as a company, we provide products and service solutions for the entire network. So different solutions for the central office, or feeder and distribution networks, drop cell sites, MDU business solutions. And if you look at the various pictures going around the slide, so we make fiber cable. You can see splitters, terminals. The coil here is a product called Easy Bend that's used in houses and different devices that go in the house. If you look also at the picture to the middle of the screen on the right hand side, it looks like molding, but that's actually a fiber deployment that uses a product called Invisalite, which is a very invisible fiber, or very low visibility fiber that is used for residential MDU type deployments. And in addition to that, we also have a product, or we have a services group that will do engineer, furnish, and install services for various networks. So products and services for the entire network. So the agenda that we're going to talk through today is, first of all, cable type. So we're going to talk through cable type, and also talk through network architecture. And so I'll just go ahead and get started. In terms of cable type, we're going to primarily be talking about the differences between all dielectric self-supporting and loose tube duct cable applications. So these are two different cable applications that are commonly used by munis and co-ops. And we consider this presentation to be a little bit beyond an introductory presentation. So we're going to assume that you have a little bit of basics around fiber and cable. But these are two different types of cables. There is ADSS, which is all dielectric self-supporting. It's often used with new builds with no strand and lashed cables. So this is a typical duct cable that's lashed to a messenger. So if you look on the right-hand side of the screen, you can see a picture where both of these are deployed on the same pole. So on the bottom side, you can see pictures where there are strands. So you can barely see the metallic strand, and then there are cables lashed. And then if you go up a little bit higher on the pole, then you can see several examples of self-supporting cables that are on this pole. So to illustrate where what these things look like, that is an example where both of them are used on the same pole. And so we're going to go through in a little bit more depth about some of the differences, some of the pros and the cons, and where you use what over another. And to kind of give an overall summary, the cable choice really depends on the application. So with ADSS, it's often a better choice when going to new networks or to new areas. There are typically lower make-ready costs and installation costs. But one of the drawbacks is that the drop management. So taking drop cables off of this cable, it's a little bit less clean. But that's often offset with just significantly faster installation. A lashed cable, this is again a duct cable that's lashed to a messenger that's typically more expensive unless a strand is available. And we'll talk about that a little bit more. If a strand's available, absolutely go for it. Lashed cables are also good choices for high customer density areas. So where you have a lot of individual drops coming off, and the situations where you may need a little bit more ground clearance. Sometimes the extra strength of the messenger can be helpful if you've got some ground clearance issues. Also, one of the downsides though with lash cables are significantly higher make-ready costs and slower initial deployments, but then that's also offset with cleaner drop management. So we, as a manufacturer with a deep background with both of these types of cables, we expect long-term reliability for either of these cable types to be very similar. And the other thing is that the solutions can be mixed and matched as needed. And just looking at these from a relative deployment cost standpoint, and this actually comes from our electric co-op solutions guide. And so feel free to ask us for that. But you can look at just some relative comparisons, and typically underground and conduit is most expensive. There are a lot of variables that go into this, and these are all just relative costs. But direct varied cables are a little bit less expensive. Aerial lashed is still a little bit less expensive, and then from aerial ADSS, just on an overall basis, is typically the least expensive option of for cable deployments. So to dive into this and the comparisons between ADSS and lashed in a little bit more depth. So the installed cost is typically significantly less expensive, and there are several different reasons for this. So first, there's one cable. So if you're installing a self-supporting cable, which means it supports itself, then you're installing basically one cable versus two. That can mean fewer trips up the pole, and it also means that the installation can be typically much faster. So this really depends on the right of way, but 1 to 2 kilometers per day is not unusual, and so it can make for a pretty fast installation. Fast installations also mean that you can get up and running with service a little bit more quickly. Another difference is lower tensions, and in certain situations that can also mean less guying, and guying actually can be a reasonably significant cost to the network. With ADSS, there's no maintenance in comparison to the lashed cable. So the lashed cable requires some reasonable amount of maintenance on a several yearly basis, where you just have to make sure that the lashing wire hasn't broken and that everything is tight. I think all of us have driven down the road and seen where the lashing wire in a lash system has broken. And so with ADSS, you don't have that, but you do have that with a lash system. Another advantage is no bonding or grounding. So, by definition, all dielectric self-supporting cable is, it's dielectric, so it doesn't require any bonding or grounding, which also means that you can place it up in the supply zone, which can significantly reduce make-ready costs. And I've heard, some really significant numbers here as far as some of the comparisons. And, so you sum all of those together, and for a lot of munis and a lot of co-ops, it can mean that the best choice, that is really the best choice for fiber to the home and building to new areas. So where to use lash cables? Absolutely, it's a no-brainer if there is strand already installed. So if you've got strand that is available to you from, the cable TV company or the telephone company, or if you are the telephone company, absolutely use that strand. That is a no-brainer. And also the situations where you have higher density areas, it can reduce some of the pole attachments. So, that it can make a lot of sense there as well. And again, we provide both. Really aren't partial one over the other, but we do see in muni and co-op areas that there can be an advantage from an ADSS standpoint. So looking a little bit deeper into the differences between some of these cables. So with a loose tube cable that is lashed to a messenger wire, it's not self-supporting, so it's not designed to support itself. It does have a 600-pound pulling tension short term and a 200-pound tension long term, with the expectation that the ice and wind, in an aerial network is going to be absorbed by the strand. So what's interesting about this cable is you expect more strain at the installation, but then once you get it up there, the strand is expected to take the load. Where ADSS is the exact opposite. It is designed to withstand wind and ice loads in the span lengths. It has, in fact, the least amount of strain in its lifetime is at installation. And then, it will see, and it's, excuse me, designed to take wind and ice loads over the lifetime of the cable. And we'll talk about that in this next slide. So how does ADSS work? So on the screen, we've got a stress strain curve. We've got actually a picture of the of the span, and we've got a spring. And the reason that we've got the picture of the spring is I typically describe ADSS as a big spring. So basically it is designed to spring back and forth while protecting the fibers, and it does that very well. And so if you look at after installation, and anywhere that's green in this stress strain curve means that the cable, we expect very, very long lifetimes. So during installation, you'll have a certain installation sag and a certain amount of strain after installation. And then for once you see ice and wind loading, so NESC light, medium, heavy, depending on where you are, or we can customize, for special wind and ice situations. We design for that. And when we're designing for that, we're also limiting the amount of stretch in the cable and the amount of strain in the fibers, such that we keep below something called a maximum rated cable load, where we're limiting the amount of strain ultimately on the fiber. And so over the lifetime of the network, then we're expected to stay in the green zone. There could be situations, maybe a truck runs into the cable, or you've got a very bad storm or hurricane or tornado where you see loads that are beyond the maximum rated cable load, and then you're starting to get into the yellow range with fibers. And then if you have just a tremendous amount of stress and strain, the actual cable can break. But this is just a look at how ADSS ultimately works, and it's designed to spend its lifetime, stretching, expanding, and contracting. So some of the differences, to the deeper design, the ADSS tube is a little bit thicker, and that absorbs crush resist. That gives a little bit more crush resistance versus a standard loose tube, and also it has a little bit more free space and excess fiber length, and so that gives you a little bit more margin before you start to see strain on the fibers. There's also a difference in the excess fiber length. So the diagram at the top shows a little bit more excess fiber length inside of an ADSS tube versus a loose tube cable, and you just have to be a little bit careful about that, because you want to make sure you control the amount of excess fiber, because if you have too little, then you can get strain too soon. If you have too much, you can actually induce attenuation issues. So whoever your supplier is needs to make sure that they have very good control over and this goes for either cable type, but make sure that they've got good excess length control in the buffer tubes. Another difference between the two are the stranding angles. You can see that there's a steeper angle, and a steeper angle will actually mean that you can stretch longer before you actually start to see fiber strain, and that uses a little bit more fiber. So you can see the mock ADSS diagram of ADSS is the top one, and then the loose tube has a shallower angle in the bottom. And then, just a couple more differences. The amount and types of strength member are important to control the stretch. So duct cables often use glass rovings. Glass is a little bit less expensive. It's also not quite as, doesn't give you quite the same performance that you have with an aramid, which is typically used with ADSS. So a short span ADSS will have you can often have a single jacket, can use aramid yarn for the strength and to limit stretch. Long span cables will use more aramid, and also can potentially use two jackets. And that second jacket, the inner jacket there, actually helps to protect the buffer tubes as the the outer aramid clamps down around it as it starts to see strain. So a couple of different types of strength systems. And to go ahead and start to wind down, the required design information includes the fiber count. So we designed for the fiber count, the maximum span. And so one note about that is ruling span, or that's not ruling span, it's maximum span. And so we're designing for the maximum span that the cable is going to handle. Also, the worst case environmental loading conditions for ice, whether it's radial or rime ice, the wind, if there's anything that we need to know about temperature or safety factors. And then also we can design the cable to actually be installed and operate within a window. And so the more aramid we use, the more stretch we can use to control, or more stretch we can avoid under loads to actually give lower sags. And so that's something we can actually control. And the final thing is line voltage. If distribution lines, we typically use polyethylene, but when we get into higher transmission voltages, then we can get into the use of a tracking resistant jacket. So that's some background around ADSS. I'm going to turn it over to Tony, and we'll be happy to talk through questions at the end of the presentation.
All right, thanks, Mark. So before we kind of get into the network architectures, I wanted to touch briefly on just the kind of the overall network plan. And, before you go ahead and decide to really dig into getting a network up and going, what you need to first look at is actually planning out the network in its entirety. And so the objectives there should, one, be to streamline the build cost estimation process. And what I mean by that is you need to understand through the planning process roughly what the build is going to cost, and that is from a labor perspective and then also from a material perspective. And again, a good plan will identify that. Next, it will also help reduce the installation cost, and there, if you've got areas that potentially can go aerial versus buried, if you've got different types of architecture that can be deployed, potentially one being more cost effective than the other, those are things that you need to identify up front, again, so that you've got the most efficient and cost effective network possible. The other thing it should do is it should help increase the speed of the network build. Again, by doing the plan up front, you've got a good list of all the materials that you're going to need, all the footages. You're going to know where all your splice points are going to be located at, potentially where your cabinets and your handholds are going to be located. So again, those are things that will help speed up the build. A lot of times you can kind of get material ordered in advance, once you get going, you can then, have everything right there at your fingertips for the entire network build. And then finally, it should also increase the return on your investment. So if you've got areas that are going to be lower cost from a deployment standpoint, and if you've done studies and you're expecting, significant take rates in those areas, those are probably areas that you want to focus on up front so that you can get that initial kind of good return on your investment. All right, next slide. And kind of so with the plan, the one thing that we like to stress and that we always want folks to keep in mind is, especially with the backbone portion of the build, is don't think about just what you need today, but think about what you're going to need 10 years from now, 20 years from now. And so you really need to be planning this network for the future. So, in the grand scheme of things, the actual fiber and the glass and the cables that are going into the network, it only represents about 10 to 15% of the total build. So, the majority of the cost for the build is going to be in your labor and is going to be in your electronics. So it's always good to kind of upsize and be prepared for what you might need down the road. And one of the things you've got to look at is how is this network how is it going to be used currently and potentially in the future? So who's your constituents? Is it just going to be going to, residential and business? Are you looking to connect up potentially hospitals, schools, public offices? Are you looking to potentially do any leasing of your network to others? So again, those are things that you need to take into consideration as you're planning this network out. And again, make sure and plan for the future. Next slide. All right, so getting into the network architecture. So there's two primary network architectures. One is a PON-based passive optical network, and then the other is a point-to-point or active E. And the difference between these two, it's actually pretty straightforward. With a PON-based network, what you're doing is you're taking a single beam of light from your OLT on a single fiber, and then it's hitting a splitter, and then that splitter is then splitting that light up amongst the customers. And so in the US, the typical splitter ratio is 1/32. You can do 1/16s, you can do 1/64s, whatever the case, but the typical is a 1/32 split. So again, you're taking that single beam of light from the OLT, and then you're splitting that light up, that signal up, for each of your customers, or in most cases 32 customers. Now with the point-to-point, it's the exact opposite. There's no splitting involved. So you've got a dedicated fiber, again, a single fiber, leaving that central office and then going straight to the customer. So again, there's no splitting involved. It's just a dedicated piece of glass, again, from the central office to the customer. Next slide. All right, and so kind of getting into the weeds a little bit with these architectures. So the current Gen GPON, what you're looking at from a bandwidth perspective, downstream is 2.4 gigabits. Again, that gets split up typically 32 ways, and then on the upstream you've got 1.2 gigabits. So when we talk about XGS PON, so that is where things are going. And where things are moving to. So the current gen, again, it's just your standard GPON, and where things are starting to move to, and we're starting to see it, is this XGS PON. And what that is doing is it's multiplying your downstream basically by 4x, and then your upstream by 10x, to where you get a 10 gig symmetrical bandwidth on the network. And then from a point-to-point perspective, what's being offered today is roughly about 100 megabits all the way up to a gig from a bandwidth perspective. You can potentially go higher. A lot of times you may need potentially to add a second fiber. And then they're also coming up with looking at ways to actually increase the speeds on point-to-point and the bandwidth on point-to-point. So one of the things that I want to touch on here is the wavelength aspect. Of going from current gen to kind of next gen architectures. And what's happening is with the increase in bandwidth is we're actually basically the wavelength is getting longer, which means that it's going to be more susceptible. So those cables are going to be more susceptible to attenuation. So when you've got your folks out in the field installing these cables, you want to make sure that they're installing them the correct way so that attenuation is lessened. And then you also want to make sure from a material standpoint that you're buying a good quality fiber and a good quality cable. All right, next slide. All right, so this is our first PON-based splitting architecture, and this is the central office splitting architecture. And so what you've got here is you've got your OLT, and then you've got your splitters located in the same location, or essentially kind of the same cabinet there in the central office. So you've got your shared fiber going from your OLT to your splitter, and then from that splitter coming out of the central office is where you've got your dedicated F2 fibers. And kind of the trick with this one is that those cables that are coming out of your central office, they're large and they're high count. And what this requires is when you hit a branch point to go, different direction, you're going to have a lot of splicing. So again, you've got large cables and you've got a large amount of splicing again out there into the network. So the kind of the trade-off or the benefit to this particular architecture is the fact that you're able to maximize your OLT port utilization and kind of your splitter utilization. So again, as customers order service, onesie, twosie, it's going to fill up, basically the first splitter in the cabinet. And then as that gets filled up, you basically then can install and then move on to your next splitter. Same thing with your OLT ports, to get things started, you're going to fire up your first OLT ports. And then as that OLT port gets filled up, you're then going to go ahead and fire up your second OLT port, and it kind of runs sequentially. So again, the trade-off with the large amount of splicing and the cost that's going to be associated with that is that you can kind of incrementally install and then turn up your splitters and then your OLTs in your central office. And this particular architecture, just given the large size of the cables and what's required out there in the field, is typically only seen in dense urban environments. Sometimes if you've got kind of a close-knit, group of maybe 500, 1,000 households, you can do this in kind of more of a rural setting. But in most cases, it's going to be more beneficial to do in a dense urban environment. All right, next slide. All right, so the next splitting architecture we've got here is a cabinet split, and so it's fairly similar to the central office split in that you've got your OLT located in your central office, and then you've got your shared fibers going out, and then it's going out to a splitter cabinet. And the splitter cabinets, the size of them can range greatly. For the sake of this, let's just assume that we've got a 288 so you've got basically nine splitters. So again, 1x32 splitters located in the cabinet, and then from there you've got your individual fiber, your F2. Again, your dedicated fibers going out to your customers. So this is the most widely used splitting architecture in the US. And a lot of the large telcos have used this. And a lot of it, I think, has to do with the fact that it mimics very closely the old copper networks. So again, somebody orders service, your technician goes out, he's going to run his jumper on the splitter cabinet, and then go out to the end customer and kind of get things turned up and running. And what this also does is it also strikes a balance from a cost perspective, to where the cost of the F2 or the outside plant network, specifically the splicing, and then you also have slightly smaller cable sizes, is going to kind of go in tandem with the cost of the electronics. And so you've got kind of this nice balance going on of cost associated with the outside plant network, and then cost with your electronics. All right, next slide. All right, so this is where we see a pretty big shift as far as the architectures are concerned. With a distributed split, you still have your OLT located in your central office, and then you've got your shared F1s going out. But instead of going to a cabinet where you've got multiple splitters located in a single cabinet, what you've got here is you've got a handhole, maybe a pedestal, where you've got a single 1x32 splitter located inside of it. And then what you're creating here are micro distribution areas of 32 customers. And so what this architecture does is it actually really reduces the cable sizes, and then it also really reduces the amount of splicing that you need to do in the network to get it ready. Now, the trade-off with this is that you've got to assume that you're going to have at least one active customer in each of your micro distribution areas. And as such, you've obviously got your splitters that are going to get installed, but then you also have to activate all of your OLT ports. So again, that's kind of where your trade-off is coming from. And what we have seen and kind of what we recommend is that if you've got a kind of 20 to 25% take rate, and you expect it to be kind of that or better, you really want to take a look at a distributed splitting architecture, or the next one that we'll get into, a cascaded splitting architecture, because you're going to see the savings out there in the field versus having to activate all those electronics up front. All right, next slide. All right, so this is the last kind of pond-based splitting architecture. So this is the cascaded split. And again, similar to the distributed split, you've got your OLT in your central office, you've got your shared F1s going out. But instead of a single splitter getting out to the end customer, you've actually got multiple. So a lot of times what you'll see is a 1x2 or a 1x4 split. And then you'll kind of break that F1 up into what we're calling an F1.5, and then that's going to hit a second splitter, and that's going to be typically a 1x8 or 1x16, depending on what the first split was. And then you've got your dedicated fibers going to your end customer. And what this does is, again, it further minimizes the cable size out there in the field, and then it also further minimizes the splicing. This is not something you're going to see in a dense urban environment, or really even in a suburban environment. This is pretty strictly reserved just for your more rural type deployments. All right, next slide. Okay, so here, this is just taking a look at the advantages and disadvantages of the distributed/cascaded splitting architecture versus your central office and your cabinet. So advantages of your distributed cascaded, again, you're going to reduce those cable sizes. You're going to significantly reduce the amount of splicing, which at $25 to $30 a pop can get pretty expensive. And then you're also going to eliminate the need for splitter cabinets, and then also the permitting that would be associated with that. So a lot of times you can have issues, negotiating where those cabinets are going to get located. And again, this kind of alleviates the need for those. And then the disadvantages, so you've got 100% splitter, installation up front, and then you've got your 100% utilization of your OLT ports back in your CO. All right, next slide. All right, so to kind of sum things up, so again, Mark hit on the kind of the big differences between, the two methods with ADSS and Lash, and then some of the advantages of using ADSS, again, out in your network. And then, again, can't stress this enough, whenever you're planning your network, again, think about not just what you need today, but about what you're going to need in the future, 5, 10, maybe even 20 years from now. And you want to really right size the network for what you potentially are going to be needing down the road. And then we also talked about the different types of PON architectures. your basic GPON, and then your point-to-point. And then we also, again, touched on the pros and cons of just your PON-based network architectures. And so with that, we appreciate the time today, and we will go ahead and open it up to questions.